Okay, so welcome to the last problem solving session in this course, Fundamental Algorithms. So this is a 4-week course. I hope that you had a good time in the course and we have seen a couple of fundamental algorithms in this course. So in today's session, we can discuss about problems that you have. If you have any doubts, then you can ask me. And I have planned for 1 or 2 questions that I wanted to discuss. So to begin with, if you have any questions, any of you, you can let me know. Any doubts, anything that you think needs clarification? Okay. So we have seen many algorithms in the course. One of them was sorting. So we have seen a couple of sorting algorithms. We have analyzed their running times, right? So what is sorting? So given a set of numbers and you want to arrange them in either the ascending order or descending order. Right? So let us say this is your input. So this is a set of numbers. Let's say we call this set A, and you're given additionally that whether you want to sort in ascending order or descending order, that is also given to you. And then you perform a set of operations so that finally you get the sorted order, right? So I've seen the algorithms, but we haven't seen any use of these algorithms. So uh, in today's class, we can see nice use of an algorithm, uh, of sorting algorithm. But before we go into the application, uh, I'd like to introduce you with the paradigm of algorithm design, which is called the greedy algorithm design. So what do we do in greedy algorithm design is that uh, I think greedy was also part of the, yeah, of course, we have seen Dijkstra and all this uh, Kruskal, these algorithms, which used the greedy paradigm. That means at every iteration of the algorithm makes a choice based on what seems right at that moment using some criteria which is greedy in nature. So still I'll take an example. Let's say you're interested in going from one city to the other. Let's say one city is Bengaluru and the other city is Chennai. So you are at Bengaluru right now. So you are here and you want to go to Chennai. Okay. And there are a couple of options for you. So you can go by road. So you can take a bus. That is option 1 for you. So you can take a train. That is option 2 for you. And you can take a flight. That is option 3 for you. So additionally, you also know that what is the cost. So how much is the price of the ticket if you go by any of these modes? Okay. So for example, let's say bus ticket is something like 800 rupees. Okay. Train ticket is something like 500 rupees. Flight is something like 3,500, let us say. So if your criteria is to minimize the cost of travel, then what you will do? So you have 3 options. You want to minimize the cost of travel. Then you will see that which one has the minimum ticket cost. Then obviously you will go with the train, right? Because it is the minimum cost. Because that is one approach. So depends on your criteria, right? So if your criteria is not to minimize the cost of travel, let us say your criteria is something different. Let us say your criteria is to minimize travel time. That could be one valid criteria. So you know that bus takes, let us say, 8 hours, train takes 6 hours, and flight takes 1 hour. Then if you want to minimize the travel time, then obviously you will take flight. Right? So depending on what the objective is, you're making a decision, and that decision is gradient. So a similar thing we do in greedy algorithms that you have seen in Dijkstra or all such algorithms which use the greedy technique. So today I'm going to give you a problem which is going to use the greedy strategy, but it is not clear beforehand that what greedy strategy one should use. So let's jump to the problem. So the problem is that you have a machine. Let us say this is a machine is at your disposal. So this machine is capable of doing something. So it's capable of, let's say it's a processor. So it is capable of doing calculations and other processing. So there are potential customers and they have their own jobs that they want to run on this machine. Okay. But there are time slots in which they want to run their jobs. Okay. So let us say we have a couple of candidate jobs. So J1 is for job one, and job one somebody is willing to run on this machine at a particular time slot. So let us say that time slot is between 9 a.m. in the morning to 12 p.m. So there is a job two. Similarly, it has a particular time slot, let us say 10 a.m. in the morning to, let us say, let's see, that is 4 p.m. in the evening. And I have some more candidate jobs. Okay. And finally, once I write all the jobs, basically the durations and time slots in which the jobs are to be performed. So the question that I will ask is the following. So what is going to be the goal? The goal is going to be to pick the maximum number of jobs uh, that are mutually compatible. Okay. Mutually compatible. So what is the meaning of mutually compatible? So two jobs are mutually compatible if their time slots do not overlap. Okay. So for example, let me first write down the durations and time slots of these other jobs. Okay. So let's say job three is between 11 a.m. in the morning to 2 p.m. in the afternoon. Job 4 is 1 p.m. in the afternoon to 5 p.m. in the evening. Job 5 is 3 p.m. in the afternoon to 6 p.m. in the evening. Job 6 is again in the morning 9 a.m. to 12. So job can be, I mean, there could be several jobs with the same uh, time slot. So there's a job one and job six, which are the same time slots. That is also possible. Right. And we're interested to pick the maximum number of jobs that are mutually compatible. So first of all, let us understand what is mutually compatible. So, so for example, I will compare job one with job two, and we'll ask, are these two mutually compatible? So job one is between 9 o'clock and 12 o'clock. So I'm plotting the time duration, the time slot on the number. And job two is what? Job two is between 10 o'clock and uh, 16, right? Yes. So 10, 16. So this time between 10 o'clock to 12 o'clock is common. So this time between 10 o'clock and 12 o'clock, this time is common for both the jobs. That means if you pick job one, then you cannot pick job two and vice versa, right? Because the machine is, let's say, capable of processing one job at a time. Therefore, since job one and job two have overlapping time slots, they are not mutually compatible. So we can either pick job one or we can pick job two. So what is our objective? The objective is to pick the maximum number of jobs that are mutually compatible. So what shall we do about this problem? So the problem statement is clear. Are there any questions about what the problem is? The input is a set of jobs and their time intervals, which you can plot on the number line. So basically, you can think of the inputs as intervals on the number line. And you want to pick the maximum number of intervals that are mutually compatible, that means do not overlap. So pairwise, uh, two jobs should not overlap any round. So if the question is clear, then we can try to think about how we'll solve it. And remember, we're interested in solving it greedily. So what greedy strategy shall we apply? So I propose a strategy, or rather, I propose a framework of the algorithm. Then we can see that how we can potentially modify that framework and uh, try different algorithms out. So here is going to be my strategy. So here is my algorithm at a high level. Just this slightly. It's going to be very simple. Couple of lines. Are there any questions? Somebody on meeting? Yes, salary. Okay. Been muted himself. Uh, so yeah, I was talking about designing an algorithm which is greedy in nature. So here's the framework of the algorithm. So you select a job, let us say job JI, the ith job. And because you selected this job, then you cannot select any job that overlaps, whose time slot overlaps with this time slot of the ith job, JI, right? So once you select it, so you are forced to reject or remove all jobs that are not compatible with this job, right? So reject all jobs, okay, that are not compatible with the job. Right? So that is uh, by definition of what we are intending to do, correct? So for example, in this case, if you have selected job one, then definitely you have to reject job two and everything is that is intersecting with job one. So between 9 to 12 is yes, this job has to be deleted. Job three. Yes, this job also has to be deleted if you are selecting job one. Is that correct? So far, so good. And then what will you on the rest of the instance, you will repeat. That means again, you will select one job and then you will delete, remove all the jobs that are incompatible with that job, and then you will proceed. So as long as the jobs are not exhausted. So finally, you will output a set of jobs, and these set of jobs are by definition mutually compatible. Uh, but is this going to be giving you the maximum number of jobs that are mutually compatible? So are you going to achieve your goal? That is the question. So what is in this algorithm? Uh, what is not well defined? So in this algorithm, uh, where do we have the liberty of uh, making different choices? So how do you implement the first step? That is the first question. Right. So how to make the first selection? So that is the first question we should ask. So the first question that I'm going to ask is that how you make the first selection. So which job shall we pick to start with? So any suggestions? So let me, for this example, let me draw the time intervals of the jobs. Then we can look at it. So I will draw the number line. So I will also write the numbers. So between 9 o'clock to 6 o'clock, we have all the jobs. What is the total duration? The duration is 3 plus 6, 9 hours. Right. So we'll divide this 9 into 9 pieces. So this is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So all the jobs are between this time interval, 9 o'clock in the morning to 6 o'clock in the evening. Uh, so let's draw them. So first we'll draw the job one. So job one is here, 9 to 12 is job one. So job two is between 10 to 16. Job three is between 11 to 14. Job four is between 13 to 17. And this is job four. Job five is between 15 to 18. Job five. And finally, the job 6 is between 9 to 12, that is coinciding with job 1. This is a setup. So this is our income, the time source of intervals, and we want to pick the maximum number of jobs that are mutually non-overlapping or mutually compatible. So in this example, what are the jobs that are mutually non-overlapping? So how do you make the first selection in this example, at least? Any thoughts? I'll let you think about it for a minute. So what if we select job 2 to start with? Let us say we take this job. Is that a good idea? So if we take job 2, then which are the jobs that we cannot select? So which are the jobs that are overlapping with job 2?
Job 3, sir.
Great. So job 3 and job 2 are overlapping, right? So how about job 1? If I select job 2, then I also select job 1. So we want the machine to do one job at a time. So job 1, if it wants a time slot between 9 to 12, whereas job 2 has a requirement between 10 to 16. You can still select job 1 if we have already selected job 2. It's impossible, right? Because if you select job 2, the machine is busy right from 10 o'clock. From 10 o'clock to 4 o'clock in the afternoon, the machine is busy. So you cannot simultaneously select job 1 and job 2 because job 1 has a requirement that goes well beyond 10 o'clock, till 12 o'clock. So it's not a good idea to select job 2 because if you select job 2, you see that you are not able to select anything other than job 2 because all the jobs have overlap, partial or full overlap with this job. So taking job 2 means you are not taking anything else. So which jobs should be selected? What if we take job one to start?
Job one can be selected.
Okay, great. So if we take job one, then which jobs we have to reject? So let us say we select job one. So to start with, we select job one as Alvin has suggested. Alvin, right? So what shall we reject?
Yes, sir.
That so job one overlaps with uh, which of the jobs?
Job two and job three, sir.
Correct. Job two starts at 10, but I cannot allow job two because I have the machine busy from 9 to 12. So of course, job two has to be deleted. And how about job three? Job three also starts at 11. So it's well before the machine will be free. So we have to delete these two things. These two things we cannot accommodate. That is correct. Since we have selected job one, we must delete job two and job three. So now at this point, so what I will do, I will say that's okay. So job six also is overlapping with job one. So job six should also be deleted, right? See, remember the job six and job one had exactly same requirements, 9 to 12. So only one of them can be accommodated. So therefore, job six is also out of the question. So we are rejecting job six as well. Correct. So I will just say that we are deleting job six from the queue, job two, not queue, from our consideration, and we are taking uh, job one. Job one. So now so far so good. Now we are going to repeat this same process on the rest of the jobs. So what are we left with? We're left with job four and job five. So job four and job five, which one shall we pick? Is there any incentive of picking job four over job five?
We can pick either job four and job five.
Right. So pick any of the two. So now let us say we pick job four. So let us say we pick job four. So if we pick job four, I mean we have made an arbitrary choice. So we pick it. Since we have picked this, we cannot pick job five because job five is in overlapping with job four. So in the next step, we'll reject job five. So now I have to mark job five rejected. So at this point, we for every job we have made a decision that whether to pick it or reject it. So what is our final solution? Our final solution is job one from this step and job four from this step. It looks like that for this example, uh, at most two jobs can be accommodated in a non-overlapping way. Is it possible to accommodate three jobs? This example. So to me, it looks like that only two jobs can be accommodated. We can pick maximum two jobs that are non-overlapping or compatible in this example. But again, the question arises, Right? How do we make the first selection? That is the question we have to answer. How to make the first selection? So when we selected J2, then we realized that that was a bad choice because selecting J2 leaves us with no other jobs. But selecting J1 was a better choice because we could take another job. Now we have to be clever and we have to ask ourselves that what is the right way, what is the criteria that we should follow to take the first job. Can we do it greedily? So how about we select that job which has the smallest duration? Okay. So here is strategy. It is strategy one for picking the first job. So what is this? What is the strategy? Uh, uh, Pick the job with the smallest duration. So in this example, J1 is the smallest duration job, 3 hours only, 9 to 12. So one more job with 3 hour duration, J3. Uh, is there any other? J5 is also from 15 to 18. So if we pick any of these three, then what will happen? So let's say if we had picked J3, J3's duration 11 to 14. Yes, 11 to 14. So if we pick this guy, then it seems like okay, we are still okay. Then we cannot take J1, J6, we cannot take J2, but we can still take J5. So we are still getting two jobs, right? So this looks like a good idea. So what do you think? You understand what I said?
So
Yes.
in case we took job 5, we will obtain solutions like job 3, job 1. No, sir.
Job 5. And then if you take job 3, then immediately you are done because all other jobs are overlapping with these two.
So
So
it overlap with job 4 and job 2 only, no, sir. Job 5.
job 5 is overlapping with job 4 and job 2. That is correct. So if you take job 5, so let's do this iteration. So you take job 5. So we are taking job 5. That means we cannot take job 4. Let's delete job 4. Job 4 is rejected, and job 2 is also rejected. Job 3 is still in the is a job 3 is still sort of within our consideration. So job 5 you have selected, you can still take job 3. That is correct. But if you take job 3, you have to immediately reject these things. The job 3 is between 11 to 14, which you are taking. So you cannot take job 1 because that's requirement is 9 to 12. So of course it's a valid solution. Job 5, comma, job 3 is a valid solution. But it is still taking 2 jobs. It's not taking 3 jobs. So our first goal is, our only goal is to pick the maximum number of jobs that are mutually compatible. So in this case, we see that there are multiple solutions. One solution is J1, J4, 2 jobs, and other solution is J5, J3, again 2 jobs. But my question is, how do we select the first job? And is there a greedy strategy we can apply? So how about this strategy that we select the job with the smallest duration? So the durations are here, right? So these jobs are durations. So I'll write a column for durations here. So this is duration. So this is 9 to 12, 3 hours. This is 10 to 6, that is 6 hours. This is 11 to 4, again 3 hours. 13 to 17, 4 hours. 15 to 18, 3 hours. 9 to 12, 3 hours. So there are multiple jobs with the shortest duration. We'll pick one of them and then we'll proceed. Proceeding is how? We'll select something and reject everything that is overlapping with it. We have a residual instance for the remaining jobs. Again, we apply the same strategy and we keep on going until all the jobs are exhausted. So will the strategy work? That is the question. That is the question I want you to think about. So now I can give you a counterexample to this strategy. Let us say there is a job, okay, between 9 to 12. Let us say this is what I call job. 3 hours. Okay. Uh, no, let's make it slightly larger. Let's make it 9 to 15. 9 to 15 I have a job. Uh, slightly more. Let's make it 9 to 40. So 5 hours. So this is duration is 5 hours. That is one job. Anyway. So there's another job which is between 13 to 15. This is job 2. And there's another job. It's between 14 to 16. The next 14 to 18. So how much is the duration? 4 hours. So this is not too scale. So maybe I will scale this down. It's almost to scale. So this is the first job. It takes 5 hours. 9 to 14. There's another job, candidate job. That is from 13 to 15, only 2 hours. Hmm, I will write it. This is 14 to 18. 4 hours. This is only 2 hours. So by this strategy, select a job with the smallest duration. Which job shall we pick? What is the first selection we make by this strategy?
Job 2, sir.
Yes, correct. Because this is the smallest. But then if we pick job 2, then can we pick job 1?
No, sir.
Similarly, we cannot pick job
Job
3.
3 also.
So that's a problem. So this strategy does not work because you know that what is the best solution? Best solution is pick job 1 as well as job 3 because they have no overlap. You can start this job at 9, you can finish it at 14, then you can give the machine to job 3, it will start at 14 and end at 18. So although these jobs are bigger, it was a better choice to pick job 1 first instead of job 2. So somebody has given you this information, and then you think that, okay, how would I? So this is a small example here you can see immediately. But if there are so many jobs and their requirements given to us, then how shall we make the first selection? That is the question. And we realize that this is not a good strategy. That if the smallest solution and hope that we are going to find a maximum set of jobs that are non-overlapping, then this will not work. Then what about finding its different strategy? What looks to be more promising?
We can start with the largest duration, sir.
Okay, so that is one strategy. So we said that select job with the largest. What happens in this case? This is the largest edition job. We'll take J1, we'll not take J2, and then we'll have J3. So what this example, this strategy is giving us uh, 2 jobs. That is the best we can hope for in this case. But will it always work? That is the question. Can you think of a set of jobs for which if you pick the largest duration job, then you cannot pick anything else? But if there's a job that starts very early in the morning and ends towards the end of the day, but there are other jobs, small duration jobs, which are in between, that be a valid counterexample. What if we pick what we were setting like this? It's a job from 9 to 16, 9 to 18. This is job one. There's another job, 9 to 10. This is job two. There's a job 11 to 12. I think that is sufficient, but yeah, we'll take another job, 17 to 18. This is job four. Then if we pick the job with the largest duration, then we pick J1. But to pick J1, we cannot pick J2, J3, and J4. But then the best thing would be to pick three jobs instead of one job, because these three jobs are non-overlapping. Makes sense. So if you're convinced about this, then selecting the job with the largest duration is not a good idea. Strategy fails as well. So then we have to think of another strategy. So how do you look at uh, the job with the least number of conflicts? For example, in this case, job two has overlaps with two jobs. So the conflict for job two is two. But how many jobs are overlapping with job one? Only one job. So the conflict for job one is one. Job two is overlapping with job one. So how many jobs are overlapping with job three? Only job two. So the conflict for job three is also one. So you pick the job with the least number of conflicts. That could be one greedy strategy, right? The job with the least number of conflicts. That could be one strategy. So in this case, what shall we do? Job two has two conflicts. Job one has one conflict, and job three has one conflict. So we'll either pick job one or job three. So once we pick job one, we cannot pick job two, but then we can pick job three. So we have two jobs picked. So that works. How about this case? So job one has how many conflicts? It overlaps with how many jobs? Three jobs, right? So job two, job three, job four. So three. But job two has how many conflicts? Only one. This guy. This is one conflict. Job three has only one conflict. Job four also has one conflict. So you can pick any one. So let's say we pick job two. So if we pick job two, we can definitely not pick job one. And then we are left with these two jobs. Again, they have zero conflict. So we'll pick job three and then job four. So we are in fact, choosing 3 jobs. And that looks like promising. That looks a promising idea. How about we implement this for this larger uh, example? So in this case, let's look at how many conflicts we had. So just write it here only. It's easy to see here. So job one was this thing. It was overlapping with this guy, job two and job three. So the job one and job two had job six had two conflicts. I'll write it down. So I'll say that they have two conflicts. Job two has how many conflicts?
Three,
This one, this one, this one, also this one, everything.
four, so four.
So, but again, job six and job one I have drawn as one, but these are two separate jobs. So, how many? Five. Everything else. So, 6 jobs are there. So, 500. For job three, we want to count how many overlaps.
Four.
Yes, this one, and 2 jobs here. So this is 4. For job four, how many overlaps?
Three.
Job five, job three, and job two. Correct. So this is 3. And for job five, how many overlaps?
Two.
Yes, only J4 and J2. So we'll say this as 2 overlaps. So then we pick the one with the minimum conflicts. So we can pick job 5 or we can pick job 1 or job 6. So that seems like a promising thing. So you see that in this solution, you have J1. So if you pick J1, then definitely you are going to have J4 also in your solution, one of them. So if you pick J1, then you reject these two things, and we have seen that out of J4 and J5, you can pick one. So that's promising. If you pick J5 also, then you delete its two conflicts, then you have two options. So you can get to a solution having 2 jobs. So basically, you can reach the optimal solution. Optimal means the best solution. That means selecting 2 jobs. So this looks like a promising idea to me. That you pick that you first count that how many conflicts are there for every job, and then you pick that job which has the least number of conflicts, and then you reject all other jobs incompatible with it, and you repeat the process. So this looks like a promising idea, but will it work all the time? Or is there a case where it will not work? Will it always work? So far, we haven't seen any example for which it doesn't work. I could draw a few examples, try to draw a few things and see whether it always works. So I think it's non-trivial to find counterexample to this strategy. But turns out turns out that it does not always work. There are examples for which even this strategy will fail. So there is a small example in the textbook, uh, which is the following, which I will draw for you. So let us say this is job one. So I'll just say one. So this is job one's duration. This is job two's duration. I mean times not. Job three's times not. Job four's times. Four jobs. Now I'll draw more jobs. So this is another job. So I'll call it job theta. I mean just this is a notation. You could call it job five. Let's call it job five. Complications. It's job five. So the job five overlaps with job two and job three. These two jobs are overlapping with job five. And a couple of other jobs I'll draw. So this is one job. Another job. Another job. So I'll give those numbers. Let's call them 6, 7, 8. Job 6, job 7, job 8. Similar thing I'll reproduce here in the intersection in this area. 6 and 8. Then we'll say job 9, job 10, and job 11. So this is a setting. This is an example with 11 jobs in the input, and you have to pick the maximum number of non-overlapping jobs. So clearly, 1, 2, 3, 4 is a solution. So you know that at least 4 jobs you can accommodate, maybe more, but 4 jobs definitely you can accommodate. They are non-overlapping, correct? But if you apply this strategy, select a job with the least number of conflicts, then which job shall you pick first? Which is the first job you will pick according to this strategy?
Five.
Correct. That is correct. As soon as you pick 5, you are forced to delete 2 and 3. Because 2 and 3 are overlapping with this 5th job. Then what are you left with? You're left with this chunk of jobs here and this chunk of jobs here. And see that all of them have a common intersection. So there is a time at which there's a time point at which all these jobs, they want the machine. So there is a requirement for all these jobs at a particular time point. So for example, here also. So at this point, so out of these 4 jobs, you can pick at most one. One job you can pick from here, one job you can pick from here. And here you have already picked this job. So you are picking 3 jobs in total, according to this strategy. Whereas you know that there is a solution with 4 jobs. Yeah. So I'll say that once again. So once you have picked this job 5 because it has the least number of conflicts, you are immediately deleting 2 and 3. So you cannot accommodate them. Now what are you left with? Then you have to pick jobs out of the rest of the jobs. So this is one set of jobs. So this set of jobs is such that they have a common overlap. So there is a time which is part of all these jobs. So that means out of these 4 jobs, you can at most pick one job. If you pick 2 jobs from this set, then definitely they have an overlap that you are not allowed to select. Similar thing is happening here. So if you're picking two jobs from this side, then definitely they have an overlap. That is how the durations are designed. The time slots are designed. So from this chunk of jobs, you are picking at most one job. From this chunk of jobs, you are picking at most one. And additionally, in the middle, you have picked at this job, fifth job. So overall, you have picked three jobs. But that is not the optimal because you already have seen that one, two, three, and four, if you have picked, then you have four jobs. So you understand why this is a counterexample. So the strategy will not work. So yeah, it's slightly disappointed now that all greedy strategies are failing. But at this point, what we have seen in the course will help us. So at this point, we'll get some ray of hope by using what is called sorting. Sorting helps us. So now I give you the strategy that solve this problem optimally. So how do you select the first job? So here is the final strategy which will work. So you select that job which finishes first. So I'll write it down. Select the job that finishes first. So each job has a start time and finish time, right? So this job starts here and finishes here. Starts here and finishes here. Starts here and finishes here. So among the given set of jobs, you pick that job that finishes first. So in this case, one is the job that finishing before all other jobs. So you'll pick one. Now, as soon as you pick one, you delete every other job that intersects or rather overlaps with one. Then again, you have the residual set of jobs for which you have to make a decision. Among them also, you pick the job that finishes first. So in this case, two finishes first. So you'll pick two. And of course, since you have picked two, you have to delete every other job that overlaps with two. So you delete five. So now so far you have picked one and two, and you are left with this set of jobs. You pick the job that finishes first, which is that one, three. So you pick three and you delete everything that overlaps with three. So basically you delete 9, 10, and 11. And now you're left with this job and you are going to take it. So this algorithm even works in this typically pathetic setting. So the strategy is clear. Right? So what does the algorithm look like? So this is my algorithm. I repeat it. So select the job that finishes first. So I'll just copy this. This is the algorithm three-liner. Select, select multiple jobs can finish first. So we'll select one of them. We'll break ties arbitrarily. Finishes first. Then reject all the jobs that are incompatible and then you repeat. So where does sorting come into picture? So where do we sort? in this algorithm, you're doing some sorting. Where is the sorting step? So there are three steps. So in which step you have sorting?
So at second step, we will do sorting.
Okay. Uh, Actually, in both one and two, you have sorting. So you have the jobs given as intervals. So jobs are sort of like this. So first job is let us say, so how we have given. So so 9 to 12. Okay. So you can think of it as so two arrays, right? So one array is starting time, the other array is uh, so you have two arrays. So this is start array. There is a start array and there is a finish array. There's a finish time and there's a start time. For job one, you have 9 and 12. So for job two, you have something. What did we have? 9 to 12, 10 to 16, 11 to 14. Right. These we had. Job two, we had 10 to 16, we had 11 to 14, and so on. Basically, you have two arrays. This is one array. This is another array. So we are asking that we want to find the job that finishes first. So basically, the finish time array we should sort in ascending order. Sort this guy, finish time array in ascending order. That means increasing order. So once we do that, so we have a ordering of the jobs in the order in which the job that finishes first, we had that job first. Okay. So let's write down these numbers so it will be easy. So for job 4, we had 13 to 17, 5, 15 to 18. The last job was identical to job 1, 19 to 12. So 9 to 12. Now, if you sort this finish array, so how does that look like? Sort in the ascending order, increasing order. So you have 12, 12, 14, 16, 17, 18. So 12 is 2 for J1. This is J6. 9 to 12, this is 9 to 12. 14 is corresponding to J3. So 11. 16 is corresponding to this. So J2. And 17 is corresponding to J4. 18 is corresponding to J5. So you know that you have to select this job, the one that finishes. But you could have selected J6, but since there's a tie, we'll make an arbitrary choice. So once you select J1, so now we're looking at our output. So how does the output look like? So you've done the sorting. After doing the sorting of the finish time array, we have picked J1 into the solution. Now, so J1 intersects which guys. So J1's finish time is this. So if you also have a sorted sequence where start times are sorted, then you can check quickly that J1 intersects which ones. So J6, J3, and J2, right? In this case, so basically you have to look at the sorted sequence of the start array as well, and then you can decide that which all jobs to delete. So basically you are right that even in job, the second step, while rejecting jobs, uh, we have to check. We may have to do the sorting, right? But in the first step also we are doing the sorting. So what happens is once we have J1 selected, so we mark it and then we will delete these two things. And then again we have this residual array here. Uh, okay, what else? J2 also is deleted, right? J2 is between the same. So between J4 and J5, which one finishes first? This one. So we'll take J4. So let's look at the diagram. Is it consistent? J1 and J4. Normal. So we get the solution, right? So sorting has essentially helped us once we have made this strategy that select the job that finishes first. Of course, then you can ask the question that how do I know that this strategy is going to be correct for every instance, for any set of jobs? So to answer that question is slightly outside the scope, but there is a proof that this strategy will work for any arbitrary set of jobs. I'm not going to go into the proof, but you can always look it up from the book, from any algorithms. You can look at forming. So you can also look at Kleinberg coverage. You can just look at J. Erickson's book. So there is a proof. There is formal proof. There is a proof that the strategy always gives the maximum set of overlapping, or I should say maximum number of overlapping, non-overlapping jobs. So in this lecture, you have seen an application of sorting, where sorting helps us. So I think it's already 1.5 hours today. So it's a bit tiring for you as well. So if you have any questions, any doubts, you can ask me. So I will be here some more time. So somebody else joins, he or she can ask me questions. Any doubts you have, you can ask me. So I'll spend some more time here.
Sir, can you give another one simple example, sir, for this?
Uh, you mean another set of jobs?
Ah, yes, sir. Simple example.
Okay. So let's look at an example once again. Basically, you have this durations of jobs. Just a second. Yeah, so let's do this. So let's say this is job one. This is job two. Job three and four. And what else? I don't know. What else should we have? This job. So let's give some start and end times, right? So let us say this is start time is 0. So let us say this is 0 to 5. I use a different color. I use the color blue. So this job is between 0 to 5. So now we're just giving numbers. So it starts at 0, finishes at 5. Job 2 is between 6 to, let us say, 14. Job 3 is, let's say, between 10 to 19. 19 is too large. Make it 17 and get 17. Job 4 is between 11 to 20. 5 is between 16, let us say 25. Okay. Basically, how in the computer, how somebody will provide this input to you, they will give you two arrays. So let's say one array is called the start array. The another array is called the finisher. That's how they have to give. They have to give two sets of numbers. Now each of these arrays have 5 elements. 5 jobs, 5 elements. So job one, job two, job three, job four, and job five. So the start of job one is 0. The finish of job one is 5, as we can see here. Similarly, I'll write for the other jobs. Job 2 starts at 6 and ends at 14. Similarly, I will fill this table, fill this array. Job 3 is between 10 to 17. Job 4 is between 11 to 20. Right. Job 5 is between 16 to 25. Is this simple example? Is this a simple example? We'll run the algorithm on this example. If you think it's a simple one, otherwise we can draw a smaller example. What do you think? Is this simple enough?
Okay.
Okay. So let's run the algorithm. So what is your algorithm? So you pick the job that finishes first. The first thing is you look at the finish array. So in this case, it is already sorted. So in this case, it's already sorted, but it need not be sorted. But it's a simple example. So we're happy. It's already sorted. So which is the job that finishes first? This is the job. That is job one. So you pick job one. So let's say I will show picking with this color. So that means job one is picked. So when does job one end? It ends at 5. Then I ask that, okay, in the array, start array, is there a job other than J1 that starts before the timestamp 5? So this is all also sorted because it's a simple example. So job 2 is starting at 6. Every other job starts later. So basically, even job 2 does not start before job 1 has ended. So we don't have to delete anything. The job 1 is picked, so we're not worried about this element now. These two elements in the array. So sort of we'll say that these two elements are gone. So now in the residual finish array, which is already sorted in this case, we identify the first job. That means the job that finishes first. That is job J2. And we pick this. That is our QD strategy. So we take J2. And then we ask them, okay, J2 finishes at 14. Is there any job that starts before 14? We see yes. Job 3 starts at 10 and job 4 starts at 11. That is also uh, identifiable from these two arrays. So we delete these two from our consideration. So basically, these two are deleted. And of course, you have peaked J2. So this is also not in our consideration, already peaked. Now what are we left with? We'll have to job 5. So that is the last job. So we'll definitely pick it because it is not intersecting any of the picked jobs. So we pick this thing. This is also picked. Now we have no more jobs. Then we can output. Finally, we can output J1, J2, and J4. Is that fine?
Yes, sir.
Okay. So I'm here a couple of more minutes. So since we have time, maybe we can just look at a high level idea why this algorithm is correct. What is the proof that this algorithm is correct, that this strategy always gives the maximum number of non-overlapping jobs. So basically we have to argue that what is the rationale behind the 3D strategy, that why you select the job that finishes first. So basically we have to defend. We have to defend our strategy. So how to do that? So we have to defend that why select the job that finishes first. So how do we defend our strategy? That is a question. So basically, we need to argue that in an optimal solution, that means in the best solution, that means uh, the set of jobs. So you basically you are selecting a set of jobs and you are claiming that you have selected the maximum number of jobs. So let us say that the algorithm is not correct, or let us say that there is an optimal solution. Let us say, suppose that there exists. So this is that there exists symbol. There exists an optimal solution. Optimal means best, or rather optimal set of jobs. That means you have a maximum number of jobs. So we are looking at the set, that how many, that which are the jobs you pick. So suppose there exists an optimal set of jobs which does not contain the job, the input job that finishes first. So this can happen. So it means that, of course, we are picking the job that finishes first. Let us say this is the job that finishes first. So look at, okay, forget this. We'll look at an example. So let us say this is the job that finishes first. Our algorithm definitely picks it because we are pretty and we are saying that I'm going to pick that job that finishes first. But there, the optimal set of jobs does not pick this. Okay, so let us say that this is our solution. We have a solution. This green thing is our solution. And there is a optimal set of jobs. It does not pick this job. It picks different set of jobs. Let us say it picks more jobs than we do. Okay. So we have picked how many? We have picked 5 jobs. This guy has picked 6 jobs. There is a set of 6 jobs, but our algorithm was not able to output it. Our greedy strategy was able to output only 5 jobs. Let us see. We are going to prove that this is not going to happen. This is impossible. We are going to prove that this scenario is impossible. So then we'll be able to defend our strategy. Okay. That is our goal. We have to formally defend what we are doing. So we have to defend this strategy, that the job that we are selecting first. Why this is always the right thing to do. So let us say for the sake of contradiction that there was an optimal set of objects that did not contain the job that finishes first. That is this job. So then what is, so in the solution, the optimal solution, identify the job that finishes first. So this is the job. So let's say we call them 1 prime, 2 prime, like that. 3 prime, 4 prime, 5 prime, 6 prime. So in the optimal solution, we did not have one, but we had this job, 1 dash. So among the jobs that the optimal solution has picked, 1 dash finishes first. So this means that one could obtain an optimal solution by exchanging 1 dash with 1 in the optimal solution. So basically, if you had picked 1, 2 dash, 3 dash, 4 dash, 5 dash, and 6 dash, that is going to be an optimal solution, right? Because 1 dash definitely finishes after 1. 1 by definition is the job that finishes first. So therefore, one could safely replace 1 with 1 dash. So what it means is the following, that one could as well pick 1 instead of 1 dash, and of course, continue to pick these things in the optimal. So what it shows that it is always safe to pick the job that finishes first. And then one can do an inductive argument to say that this greedy strategy indeed outputs the maximum number of jobs. So this is what we call an exchange argument. So I just gave this argument high level idea and the strategy because there was time, because this is not part of the syllabus. So the idea of this session was to show you an example of where sorting is useful. You have seen many different sorting algorithms. So this is a place, an application uh, where sorting helps us. So if you need to understand how we define the strategy, that's absolutely fine. So this is additional. So if you have no questions, you can as well drop from the call. I will spend some more time here if anybody joins and has a question to ask. Okay, I think there are no questions from your side. So thank you for joining the express session today. And I wish you all the best for the exams and a happy learning.